Welcome everyone. I am Javad Fotouhi from Johns Hopkins University, and I'll be introducing reflective AR displays and their role in improving robotic workflows in the future operating rooms. Robot-assisted surgery has shown to improve patient outcomes, reduce complications, and shorten recovery time for several clinical applications. Now, while increasingly configurable robotic arms can maximize reach and avoid collisions in cluttered environments, positioning them appropriately during surgery is complicated. When the robot links are positioned suboptimally, the likelihood of collision and inadequate reach during teleoperation increases. Despite that, safe robot configurations can be computed based on the kinematics, safety regulations prevent automatic driving of the arms. So in this work, we're looking to address these challenges regarding robot arm setup. As we said in the previous slide, quick and accurate setup of robotic systems leading up to surgery remains a major challenge in the endeavor of making robotic surgery standard of care. In modern robotic systems, such as the Da Vinci Xi system, as shown in the figure, the setup of the arms can be supported by lasers. The problem is that laser guidance can still exhibit challenges in a complex system with joint redundancies, as it does not directly show the desired configuration for all joints. As most manual methods are error-prone and induce a steep learning curve, we investigated an augmented reality solution for guidance during robotic setup. Using an optical see-through head-mounted display, setup staff can be interactively guided through joint-by-joint steps to optimally position the robot in an efficient manner. In our solution, a virtual model of the robot needs to be rendered at the appropriate pose such that the real robot can be aligned with it. Now, to render the virtual robot at the right location and orientation, we need to first calibrate the virtual environment to the real world by aligning a virtual robot with its real counterpart. Therefore, we first perform virtual to real alignment to calibrate the two worlds. And after that, we do real to virtual alignment such that the robot links could be navigated to the desired configuration defined by the virtual model. In performing virtual to real alignment, the main challenge remains the perspective ambiguities that you see in the video that hinder such collaborative robotic solutions. Now in the video, we see that despite that the alignment is achieved in the user's initial perspective, as you can see, it remains still misaligned in other views. To overcome this challenge, we introduce a novel concept for intuitive alignment of AR content to their physical counterpart by providing a multi-view experience via reflective AR displays. Our method enables a user to create and view multiple AR mirrors which show the current 3D scene, including the real and virtual, from different viewpoints. Using this system, users can visualize different perspectives while actively adjusting the pose to determine the registration transformation that most closely superimposes the virtual onto the real. For virtual to real object alignment, the results in the table indicate an average error of 16.5 millimeter when using the reflective AR display and 30.2 millimeter when using AR without the additional reflective view, which is equivalent of over 45% improvement in the alignment accuracy To compute a geometrically relevant pose for displaying these images, the associated observer pose with respect to the coordinate frame of the AR scene in the operating room is computed via SLAM. After that, we construct a reverse frustum. To give rise to a mirror-like AR display, the 3D virtual structures are all projected into the image plane with the imaging geometry of the reversed frustum as shown in the bottom left equation, thus enabling joint visualization of both real and virtual in the reflective display. During the surgical AR experience, the virtual model of the robot is first visualized at a known configuration. The alignment between the real and virtual is established in multiple views via reflective AR displays. And once the 6 degree of freedom rigid body transformation is identified between the real and virtual content, a virtual robot is rendered into the scene at a safe configuration. And then the assistant can align the robot with the virtual counterpart and dock it to the trocar. In a simulated surgical setup, we assess the errors in moving the robot joints to achieve a desired joint configuration using AR guidance where a trocar must be inserted at the mannequin's umbilicus. We report the performance of 8 users in repositioning the robot joints using AR reflectors, and compare the outcome to an interactive display as our non-immersive baseline. Results suggested that guidance using AR with or without reflective display yielded significantly lower errors compared to the non-immersive fixed display. The AR guidance approach using reflective displays outperformed the AR system with no mirrors. However, in this comparison, no statistical significance was achieved. Though AR-based approaches yielded slightly longer calibration and execution times, we hope that the AR support can minimize the overall jump time by resulting in more optimal setups and therefore eliminating the need for readjustments. Our results also indicate that repositioning of the revolving joints in all 3 methods are consistently more accurate than the twisting joints. We hypothesize that the higher errors in the twisting joints are the result of the inherent symmetry in twisting motion that may lead to these ambiguities. We hope that similar multi-view strategies can be applied to simplify the alignment in other applications too. For example, here, as we see in the video, a common example of AR-supported computer-assisted surgery is shown, where surgical tools must be aligned with the virtual planning. And again, as shown in the video, it is challenging to achieve alignment from all views. We summarize the contributions of our work as first, reflective AR displays as the multi-view and marker-free paradigm for co-registration between the virtual and real spaces. And the second one, using augmented reality for effective guidance during robotic setup and enabling intuitive interaction during surgery. Thank you all very much for your attention.